Yes, I'll start today a series of 3 lectures. The purpose is to talk about artificial intelligence. I definitely don't have the answer to many of these questions, but the purpose is to invite you to think about some of these issues. Actually, sometimes nobody has an answer to some of these questions. My lectures are divided into 3 parts. In the first part, which is today, it's mainly about machines that think. I'll talk about the notion of singularity, and obviously, apparently, you saw some of that. I'll talk about my perspective on the singularity, and I'll also introduce the notion of big data. Anybody knows about big data or heard of big data? Yes? Okay, so actually the term is becoming so common in all magazines, newspapers. People talk about big data, but they don't know what big data is. I'm not talking about the readers, I'm talking about the writers, the journalists who talk about big data. So I'll introduce that notion here. In my view, big data will play a significant role in this notion of singularity. In the second part, so on Thursday, I'll talk about artificial intelligence, the concept and the applications. I'll also talk about expert systems. And finally, next week, I'll be talking about machine learning, how machines learn. And I'll talk about data analytics and data mining. Okay, let's start with something entertaining. A warning from Stephen Hawking. So like Dr. Solis said, there are some alarmists, I would say. And Stephen Hawking recently, in a column, mentioned the following. He said, the development of full artificial intelligence could spell the end of the human race. Whoa, that was shocking to many people. I mean, Stephen Hawking is a very respected researcher. He's a physicist, astrophysicist, cosmologist, you name it. He's famous actually for many theorems. Among them, the gravitational singularity has nothing to do with our singularity, but still it is called the singularity theorem. So he's very respected, and he throws this sentence at the world. People said, wow, he must know something. Actually, if you read it carefully, it may not mean what you think it means. First, he mentions full artificial intelligence. We have yet to define what artificial intelligence is, let alone full artificial intelligence. And then he's talking about the end of the human race. That doesn't mean that the full artificial intelligence, whatever that is, will attack the humans and eliminate them, and it'll be very aggressive. That doesn't mean that. And actually, on follow-up interviews, he tried to clarify it. And in one of the interviews, he mentioned the fact that because this full artificial intelligence will evolve very rapidly, as opposed to the human that evolves very slowly, I mean, that natural selection basically will make the human disappear, like in any other race. So he's talking about the human race. Now, whether that artificial intelligence will be aggressive towards the human, that still remains an interesting question to answer. So here's the entertainment part. Let's see an interview by John Oliver interviewing Steve Hawkins. Who has seen this interview? Actually, it's very interesting. So I'll show you that. So if you want to see the rest of the interview, I invite you to go to see that URL. It's actually quite entertaining. So, is that possible? Is that what Hawkins is claiming? Is that possible, or is it just paranoia? The reality, when you look at computers today, actually they can't even recognize kittens in photos and pictures. There was a project recently by Google using what they call deep learning to look at the millions and millions of pictures that they have in their databases to learn to recognize a cat. And when they finally, after millions of iterations with all these big computers that they have in parallel. When they finally taught a computer what a cat was, that was a big deal. They wrote about it in all the newspapers. So the computer today doesn't recognize a cat. A baby, human, can recognize a cat immediately. I mean, it doesn't take a long time for a human baby to recognize and distinguish between a cat and a toy and a dog and another human. And another very important thing, actually we don't even know about our own brain, and we don't know how it functions. So how can we simulate it, and how can we put it in a computer so that the computer becomes better than us? So we're still way behind. Yet, Hawking wasn't the first to be an alarmist like this. I mean, I have an example here from an eminent researcher, a very famous, Ray Solomonoff. He was actually part of the first conference, Dartmouth conference, where they defined artificial intelligence, where artificial intelligence was born in 1956. And in 1967, he said this following famous sentence: although there is no prospect of very intelligent machines, and I remind you, this was in 1967, in the near future, the dangers posed are very serious and the problems very difficult. It would be well if a large number of intelligent humans devote a lot of thought to these problems before they arise. So basically he said we should think about it so that we know what to do when they arise. One thing that he's famous about, and I agree with that, he said when artificial intelligence will become intelligent, I mean like us, it'll happen suddenly. Suddenly we'll realize, oops, that machine is actually intelligent. But we're not there yet. Okay, so the point that we have to remember is that we should devote some time and energy to think about these issues. Okay. Now, what's a thinking machine? What does it mean that a machine thinks? And what does it mean that a human thinks? What is thinking? I mean, we haven't even defined thinking yet, and there are many people who are doing meta-thinking, thinking about thinking, and trying to define what that is. So thinking basically is reflecting on situations, using information from our experiences, and we reason about that, and we make some logical, rational decisions. That's what thinking is. So some people also define it as having a conscious mind. It means being aware of what's around you, having perception, sensation, having memory, feelings, fantasies. All that is part of thinking. So humans exhibit this trait. They think rationally. They have a conscious mind. Do animals? And many people claim, yes, they do. When you look at your pets, they think. Can machines think as well? So in that case, can we program that thinking in a machine? Because the machine doesn't do it by itself, we have to program it. Can we program that thinking? So in order to program it, we have to first define it properly and express it in small instructions to be able to program it in the machine. But if we manage to program a machine to think, does that mean that the machine is intelligent? There may be two different things. And if it is intelligent, can it become more intelligent than a human? So these are a series of questions, and they cascade one after the other. In the past, machines have managed to beat humans. And here are some examples. I'll give you 3 examples. 3 examples that are very close to us. And you'll see why I'm saying they're very close to us. Because, for example, in 2007, the game of checkers was solved by Jonathan Schaefer and his team. It's our current Dean of Science. It was solved here at U of A. What does that mean? It means that you cannot beat a computer at checkers. There's no way on earth. The best you can do is a draw. The computer will win at all cases. In 2011, you probably watched how IBM Watson, the program, beat the best humans at the game Jeopardy. That was phenomenal. That was actually one of the reasons Dr. Solis was thinking about creating this course. Last week, it was announced and covered by the media worldwide that here at the University of Alberta, we also solved the heads-up limit Texas Hold'em poker game. This was announced last week. It was actually solved at the end of last year, but it was announced by the famous journal Science last week, and after that it was covered really worldwide. What does that mean? It means that at this game, Texas Hold'em heads-up limit means we have two people. It's the simplest version of the poker game. You can't beat the computer. The computer will beat you. I mean, if you play once, yeah, well, there is the chance of getting the wrong cards, but if you play enough times, the computer will beat you at all cases. This is phenomenal. Does that mean that the machine is thinking while doing these incredible things? Well, humans have tried to build machines that think for centuries. This is not new. It's not just starting with computers. Here's an example. So this is in the 17th century. A Hungarian engineer built this for the Empress in Vienna, the Hungarian Empress. He built oops, I'll go back here. He built a machine that supposedly can play chess. So you have this, it's called the Turk. You probably heard the program Mechanical Turk from Amazon. So there are tasks that only humans can do, but you can send them to the computer, and actually there are humans in the background that are doing these tasks. They're called the Turkers, and it's a program called the Mechanical Turk. It's based on this idea that this Hungarian built a machine which is actually a hoax, it's a fake. You have a mannequin wearing like a Turk, and it's playing, the arms are moving, and it's playing chess on a board. And you can play against it, and actually it's a very good player. Why? Because hidden inside that box was a master player, master checker player, and chess, sorry. And he was moving the mechanics underneath. But the reality is that, even though that was impressive, what is impressive for me is actually building that machine that managed to fake a real thinking machine. But the reality is that we don't know how we think and what does it mean to think. Well, since the 17th century, things have changed a lot. And just looking at the last half century, computers have evolved significantly. So now we don't have just mechanical machines, we have electronics, and in half a century, computers evolved significantly in terms of size, in terms of speed, and actually the Moore's law, which says that it's not a law, it's just an observation, but it ended up being a law that endured for a very long time. Every 2 years, basically the number of transistors on a chip double. And often it was actually faster than 2 years. It's incredible. Here I have some information about the sizes of the transistors and the number of transistors, so the density on a chip. And it's increasing very rapidly. So in the 70s, for example, a transistor was 10 micron. Now it's 0.045 micron. That's in 2007. Actually, in 2012, they managed to build a transistor with a single atom. So it's really, really, really small. In 2012, the density was 1 billion transistors on a single chip. Today, they can put more than that. So that's phenomenal. This progression is mainly for the hardware. So the hardware is way faster, cheaper, and so forth. but the software is not going as fast. The software is what makes the hardware do something. So the hardware alone is just hardware. You need that software to make the whatever thinking is. We haven't even defined it. Okay, just to put things in perspective, maybe, well, you're certainly not 50 years old, so you haven't witnessed this progression, but just to put it in perspective, do you know what this is? Have you ever seen this before? Maybe if you went to a museum. Okay, I'll open it. Have you seen this? Okay. Okay. There were bigger ones. There were way bigger ones, like this. Well, that's a floppy disk. A floppy disk was used to store information. And this came out, this small version, 5 1/4 inch, came out in the 80s. And I was a student, like you guys, at that time, and I was writing my thesis. On one floppy disk like this, I have the operating system, the word processor, and part of my thesis. I didn't have enough space, I had to use a second floppy disk. That was a lot of space, but actually it's ridiculously small, and this is the perspective I want to give you. So the 5 1/4 inch double density was 360 kilobytes. In 2 years later, IBM managed to increase the density. Now that is called high density, not double density, but high density, and they reached 1.2 megs. That's the one that I used for my thesis in the operating system, so on 1.2. Do you have any idea how much it costed, this floppy disk? In the 1980s, $3 for the double density and $5 for the high density. Well, not a long time ago, I bought a flash drive, 64 gigabytes, and I paid $32. That was in 2012. That means that purchased in the 80s, that would have cost me $500,000. So this gives you an idea, the progression is phenomenal. I'm not talking about 1950s here. Okay, so what is 64 gigs? What does it mean, 64 gigs? What is gig? Okay, we hear it all the time because you buy your phone has X gigs, you buy your laptop has X gigs. We're so used to it, we don't even know what that means. Well, just to give you an idea, a gigabyte is 10 to the 9 bytes, so it's a billion bytes. What's a billion bytes? We don't know. So visually, this is how I represent it. Imagine you have an Olympic swimming pool. The Olympic swimming pool is 50 meters long by 25 meters wide. It varies in depth, but there's a minimum depth by FINA, which is the international body that regulates swimming in the world. And based on that minimum depth, it gives you about 2,500,000 liters in that very large swimming pool. If now you know that in a liter you have, in a liter you have 20,000 drops, that gives us 50 billion drops. So you have 50 giga drops in that swimming pool. Now you have an idea. If you want to fill that pool drop by drop, that's how many drops you need. And that's 5 gigabytes now in that small USB drive. And now you have an idea how much you can put in there. That's huge. So other people have, this is the analysis I've done, but there are other people have done the same analysis. They have access to other data. This is a picture in 1956. They were taking a hard drive from one place to another. In Pan Am, it was such a big deal that they took advantage to make a photo op. We have the captain of the plane pausing next to that IBM. I think it was an IBM rack. Yeah, it was an IBM rack with 5 megs. They were shipping it to a customer somewhere. 5 megs. That was $120,000. The 5 megs in consumer price index, that means it's $1 million today. Okay. But today, the 64 gigs, this small micro SD card, you can buy it for $60. And that means it's 65,000 times that 5 megs. So imagine 64 gig, that small tiny SD drive, if we had it in 1956, it would cost billions. It's unthinkable. That tells you the progress is phenomenal. So I can scare you even further. Recently I was in China and I bought this drive. And this drive has, you can't see it there very well, it has 2 terabytes. 2 terabytes in here. It's actually scary. I was like, what if I lose it? I lose 2 terabytes. It's a lot. What's a terabyte? What's a terabyte? A terabyte is 1,000 gigabytes. So I can put 2 trillion characters in here. This is the screenshot of when I used it the first time, and unfortunately, I managed to put some data in there, and after a while, I burned it because the technology actually is not really ready for that capacity, and the chip burned inside. So it's not useful. But today, you can buy safe USB drives up to a quarter of a terabyte, which is phenomenal. Okay. So again, this is hardware. It's not software. It's something you can use to put stuff in it. It's like a container. But you have to make it smart, and to make it smart, you need the software. There is another world also that progressed very rapidly. Not the world of computers, but the world of smartphones and phones. Who remembers this phone? So this phone used to be called the brick because it's the size of a brick. It was 2 pounds, almost a kilo, very heavy. Do you know how much it cost in 1983 when it came out? Motorola produced this. It was $4,000. 4,000 is a huge luxury. I mean, who can afford a phone? Of course it was expensive because it's a phone you can use everywhere, anywhere you can go, where there are cell towers, actually. You can't go anywhere, but and there were not that many cell towers. The phones progressed significantly since then, since the 80s. And now we're talking about smartphones. Phones that are smart because they have some software that allows them to do some applications. They're actually so smart that now they have specific applications, and well, this course is in the catalog and for pathology, so it's in medicine. I'm showing you some examples of applications in medicine. Here's an example where you can look at the heartbeat and detect arrhythmia. Another application for ultrasound. So you can add some components that you can attach wirelessly over the wire to the phone, and you can have other applications. Here's another device where you can measure blood pressure. You can also add another device to it, and you can do eye exams with your phone. So these phones are becoming really sophisticated. Another one, you can do actually ear exams for ear infections. You can look at medical images. Maybe you can do your diagnostic for I don't know, in pathology or radiology on the phone. And it is happening right now. Here's another application for oximetry. There's an application where we participated in my lab anyways, to share images so that when the expert is far away, you can share information, and the expert can dictate or direct how the operation or surgery is taking place. Those who know about Star Trek or are fans of Star Trek and watch Star Trek, they know about the tricorder. That was like looking in 2400. Well, the tricorder already exists. There are people who build their own additional devices that you can add to the phone, like this example. This is an engineer from NASA who built his own sensor, and he had attached it to the iPhone, and he can detect rare gases and different dangerous gases, toxic gases in the air. Okay, and now we go beyond the phones. Now we're talking about smart watches. Watches that can do very sophisticated things, and you can program anything you want in them. So the hardware improved significantly. Okay, and now we have many small devices spread in everywhere that are connected with each other and can communicate. And we talk about the Internet of Things. It's not just the Internet; it's the Internet of Things. So if you have good software that can allow this hardware to communicate and hopefully think, and in addition you add what we call big data, and I'll define what big data is, this is the recipe that will take us hopefully to what we call strong AI. So Hawking was calling it full AI. Our terminology is mainly strong AI. We have strong AI and weak AI. Today we're still in the weak AI world. But we will reach the true computational intelligence, and that's what we call the singularity. So you need these 4 components or ingredients in your recipe to reach the singularity. So what is the singularity? I understand that you covered that in the past, but this is my view of things. So singularity is a concept that existed before. It exists in math, it exists in physics, and in other fields. So what we call technological singularity is basically the point when computers are as smart as humans or slightly smarter than humans, more intelligent than humans, and they start driving the technology. We don't drive the technology anymore, they drive the technology. That's why Hawking talked about the last invention, because we invent that machine that is smarter than us. That machine takes over to invent other things. We don't have to invent anything anymore, it'll invent it for us. Okay. But because it's smarter than us, the way it will drive the new technology is not something we can foresee. We cannot imagine it. And that's why, and it'll go very fast, and that's why we call it the singularity, technological singularity. So it's a recursive self-improvement. So the machine improves itself is better, it'll improve itself, and so forth. Okay. And the rate will be so fast that we can't even imagine to control it. Is that science fiction? Should we just dismiss it, say that's just in the movies, or should we think about it and actually maybe prepare ourselves for it, or maybe help it, or stop it? Okay. So these are the questions we ought to ask today, not when it happens suddenly, like Ray was saying. It's today we have to think about it. So here's my argument why philosophically it may happen. Practically, it may happen too. The question is when. Some people are saying it'll happen actually very, very, very soon, in a matter of 2 decades or something. I think that I will not see it myself. Maybe my kids, maybe after. So here's my reasoning. If you look at a mouse and the world of a mouse, is the mouse thinking? Is the mouse intelligent? What do you think? Is it intelligent? Yeah, it is intelligent. Well, if it rains and it's flooded and it needs to go to the other side to find food, it'll swim. It'll think about swimming and crossing that obstacle and go to the other side to survive. Okay, so it adapts to its environment. It's self-aware. It knows that it has to survive. It knows that to survive it has to go to the other side, and it finds a solution to that problem it has. When it finds food, it'll eat it. And if it's not cheese, if it's not something else, it'll adapt to it. When it has little ones, it needs to build a nest first. If it's in the field, it'll use whatever is in the field to build a nest. But if it's in my garage, it will use something else. The paper, the cardboard, the plastic, whatever it'll find. And I had that problem before. So it will adapt. Actually, if you take a mouse in a maze and you show it, you let it in the maze and it finds its way finally to get that reward, the piece of cheese. If you take it to the start again and let it go, after a while it'll learn the maze. It'll find its way very rapidly. It doesn't go in these cul-de-sacs. So it memorizes and it learns from experience. You can actually argue that the mouse can even count, can do additions. I have 2 little ones here. I had 3 before. 1 is missing. I go and look for it. Okay, so it can count. It can do some simple arithmetics. You can teach it, like people teach dogs or cats or whatever to count. But now let's continue to look at the mouse, but in another environment, with another perspective. When the mouse gazes at the stars, do you think the mouse thinks about planets and ponders whether other mice exist on other planets and things like that? Probably not. It doesn't see, so even though it has awareness of its environment, it doesn't go beyond what it can touch and smell. Again, this is a speculation on our part, but it's logical speculation. Do you think the mouse also thinks about the structure of the proteins, like we do? Do you think when the mouse goes to my garage and finds, for example, the insulation in my engine and rips it off to build its nest, do you think it has an idea what that engine is for? Probably not. It's just warm. When the mouse hears this thunder outside because the rocket is going up to space, it has no idea why we're doing this. And the mouse certainly cannot think abstractly with math like we do. What does that mean? So you agree with me that that mouse is intelligent, but it's not intelligent enough to understand what's a protein, the structure of a protein, what's an engine for, and MC square, it doesn't understand these things. So it means that it's not intelligent enough, it's not as intelligent than us. So we humans are superior. And indeed, humans dominate on Earth not because we are strong. Other animals are way stronger than us. But we are ingenious. We can build tools. We can adapt better than others. So when you compare the humans to the animal, we are intelligent. They are intelligent, but they are sub-intelligent. They are less than us. So that means I can build actually scale. Starting from 0, the human, there's the sub-intelligent, like the mouse and others, but they could be super intelligent, more intelligent than us, in the plus side. And like the mouse, cannot understand and comprehend our intelligence, we cannot comprehend the intelligence that is superior than us. We can only imagine that it exists, but we don't know what it is. We don't know what it is capable of, because it's beyond our level. Okay? So that's about singularity and super intelligent machines, these hypothetical machines that I believe one day will happen. So what about big data? What is big data? So big data comes actually, it's very recent. Even though many people heard about it, it's very, very recent. In 2008, in Wired magazine, there was an article talking about the fact that what we called big collections of data, big data sets, is not big anymore today. So I remember when I started working on data mining in the early 90s, when we worked on data sets the size of some megabytes, that was a big deal. Today, megabytes is nothing. So we're talking about working on terabytes, even bigger than gigabytes. So the notion of what is big is changing. That's what that paper talked about. In that same year, a white paper came out by 3 eminent professors in databases and information retrieval, and they mentioned, okay, now big data, this term, let's define it, and they called it something that is so complex in terms of data. The data is so complex that the current tools that we have cannot handle it. Tools for storing it, tools for managing it, tools for searching in it, tools for analyzing it, and so forth. And they gave examples. We need tools like machine learning. And I'll define later machine learning. We have a section for it in order to analyze this data. Okay. And from there, people started using big data, well, actually, it was an anarchy the way it was used. People are using it without understanding, and they just kept the term big. In the reality, the big data refers to massive, indeed, it's big, massive amount of data, but it's complex data, and it's difficult to understand and manipulate with the current methods that we have. We need to develop other methods. So later, IBM defined it in their terms. These are the guys in the marketing department of IBM. They defined it more precisely, and they said we have these 3 dimensions. Later, they became 4 dimensions of big data, all starting with V's, and they call them the 4 V's of big data. So the 4 V's are volume, the size. It's very big. So it's not just the size, big. There's the other V's. The second V is velocity. This data is coming at you at a very high speed. So you see it only once. You don't have the luxury to see it a second time because you have more data coming at you. Then you have the variety, another V. What does it mean, variety? It means the data is coming from different sources. It's not just one source, it's coming from many sources, many different silos. And there's also variety in the data itself, and I'll get to that later. And then finally, there's veracity. Veracity is making sure that the results that you get down the road is true. And the way because of the uncertainty in the data, specifically if it comes from different data sources and you don't have control over these different sources, you need to manage metadata that has to journey with the data till you analyze it at the end. So basically, big data, you have the size, but it's not just the size. You have the velocity, so you have a fire hose of data coming at you, and you have variety, so coming from different places. And in addition to the 4 V's that IBM is talking about, actually I added other V's. There's value, and the value comes from the integration of the data. And there's also vulnerability. Vulnerability has to do with privacy of the data, because sometimes you have the privacy preserved in this data. Privacy is preserved in this data, but when you put them together, then the privacy is jeopardized unbeknownst to the custodians of both data sets. Anyway, so what you have to keep in mind is this, in addition, the variety in the data itself. We don't deal with just numbers anymore. So we have images. We have a lot of images. We collect a lot of images. We collect videos. We collect sound. And in addition to the sound, we collect a lot of text. Imagine all the emails, the tweets, everything people write in these social media thing. We have also the connectivity between objects. Things are not independent, they are related to each other. And what is capital in big data is the integration. So because you have this variety of different data sources, it's when you put them together that you get value. So the value is in that data integration. Here I'm representing them with different pieces of the puzzle. It's when you put them together, so you have data acquisition, extraction, data cleaning, representation, and so forth, all these tasks that have to be done. And then finally, you do the interpretation. And it's by putting all these pieces together that it'll help you do a better interpretation, and you get the big picture. And where the veracity plays a role is the metadata that you have to carry with you. For example, looking at this picture, in order to interpret it, I have to know that it's in the fall that leaves fall. So that's fall season because you have colors. You may look at the architecture, and I have metadata about architecture, so I can interpret it saying that's in Asia, it's in China, and so forth. Okay. So I'll give you some stories, anecdotes to show you the importance of this data integration. Maybe it'll give you a better idea about what is big data. A few years ago, in 2006, Netflix, do you know the company Netflix? At that time, they were not online. They were renting DVDs that you can mail by the post. And they built a recommender system to recommend videos or movies to their customers. The recommender system is based on an algorithm that they developed called Cinematch, and it uses the ratings that the customers put on all the movies that they watch. Okay. So they build a recommender system that exploits a matrix. That matrix has all the movies and all the customers. And inside the cell of the matrix, you put the rating. This customer liked or disliked this movie. They have stars, 1 star, 2 stars, 3 stars, up to 5 stars. Okay, that's the data that they have, and they use that to recommend a new movie that the customer hasn't seen. But they couldn't improve it more than what they did. They spent a lot of time, they couldn't improve it more than that. So they created this challenge called the Netflix Challenge, $1 million prize for whoever manages to improve their algorithm by 10%. And they provided the data. Here's a set of customers and set of movies, and here are the ratings. Show me that you can do better than 10%. Well, it took a long time. Very quickly, actually, they did better than Cinematch, but it took a very long time to beat that 10%, actually improving the error rate by 10%. So the cream of the cream, the best of the best in the world, were trying to do it, because $1 million is a lot of money. And in the beginning, they thought, well, that will be easy. It wasn't easy. Because of the constraint that Netflix gave. They said, use this data. That's what I use, so that's what you use. After 3 years, when finally the teams actually went together and they combined all their solutions and they beat the 10%, Netflix never implemented it. They scrapped it. They gave them $1 million. Actually, they did an incredible publicity with that. They got way more than $1 million. But they scrapped it. Why? Because it was so complex, and because had they used other data, for example, IMDb. Do you know the website IMDb? It has all the information, well, a lot of information about the movies, the genre, who's the director, who's the actor. If you use that information and you build the relationships between the different movies, you can get way better results than just being stubborn on that matrix. So integrating extra information that doesn't necessarily belong to you. It's public, it's outside. If you integrate it, you get better results. Here's another example, very quick example. This is a hypothetical company that sells plans for the mobile phone. At the end of each month, they will look at their customers to see who ended his plan. Should I actually give them incentives to stay, or they can go to the competitor, I don't care. Okay. So hypothetically speaking, this is a hypothetical situation, as I said. I have, 19 customers here that finish their plan, and I look at my database. How much money did I make in the last 3 months on these people? Okay. So I have a column there that is called average 3-month profit. So I can sort that, and I can see I lost money on some people, and I made a lot of money on other people. So I can say, if I made less than $50, I can let them go. While the others, where I made $1,000 or $2,000, I'll give them an incentive, free phone, bonus minutes, or whatever. Okay. Does that make sense? It seems a logical kind of decision. It's the wrong decision. I'll tell you why. So rather than taking the top and say, well, these guys, I didn't have enough profit and I let them go, that made a strong assumption that the people in my database are completely independent from each other. But they are dependent, they call each other. So what I'll do, I look at the whole database, these 19 people that finished their plan, I will look at who do they call. Okay, so I have here 34 more people, and I can draw the graph of who calls who and for how long. And I can put these 6 people that I wanted to let go, I put them on the graph and see how important they are. It's very difficult to decide. I can drill down, and I do what we call community mining. I will find the communities of who calls who inside that community and less outside the community. I will not go into details, but anyways, the point is that I will cluster them into groups, and I will place these people, and I'll see 2 of them are in the purple group, 4 are in the yellow group, and then if I visualize them, and this is important also in big data, visualization is extremely important. I visualize them in a concentric circle like that, and I'll try to see where do they place. And I'll see some are peripheral, but others are very central. So this guy that I wanted to dump, actually it's Natalie, I said, I don't care, I'm not making a lot of money. Actually, if she leaves, she may influence the whole group, and the whole group will leave. In that case, I will lose $3,000. And the other group, same thing. I have some people who are peripheral, but one guy is very central. He's not the center, but central enough that he can influence the others. So my decision now changed. By looking at extra data, not just that table, by combining the data, now I have a different decision. Actually, 4 of them, I let them go indeed, but 2 of these guys, I will give them incentive, a free phone, so that they stay. Okay. So this shows you that big data is about integrating. It doesn't have to be just the size. It's the fact that you have this variety, and you integrate it, and you have more information than you had before. So now companies are doing this. Here's an example that will scare you. Companies call it the DNA of the customer. So suppose I have a company that sells things. I go in, I register. So I register, I volunteer information. I put it in green. This is the registration information. I say my profession is this, I live in this place, my age is that, I was born here, whatever, all this information that they ask. I volunteer that. I believe that's what they know. But then they look at what I buy. For example, I purchased a watch that I can use for swimming. Oops, he's a swimmer. I used goggles. Oh, it reinforces this information about swimmer. I never told them that I swim. I bought helmets. Oh, he has a bike. Maybe he does triathlon. Now they start thinking about advertising for running shoes or things related to my activities. I bought, but there's an important point here to make. There's sometimes very strong uncertainties. I bought a coffee machine. It's not necessary for me. I may buy it to give it as a present. Actually, I don't drink coffee. So they have to also manage these uncertainties. But they go beyond. They look at how I review these products, what I liked, what I disliked, how often I answer the reviews of other people or comment about other things. If they have a community inside their store, how many friends do I have? All this information, I didn't know that they were collecting. I thought the only information they had is the registration information that I gave them. But they go beyond. They will do web searches, and they will go and check social media, my friends, what my friends like, not just what I like, what they like. And what they like can tell a lot about me. Believe me, you'd be surprised. They will look at the microblogs, Twitter. They will look at LinkedIn, the past professions, where I lived. They will look at where I went with Foursquare. They will do searches on search engines. Are there articles about me? The images, the videos. Did I actually edit some things on Wikipedia? The news, the blogs, do they talk about me? Or did I participate in blogs? All this information, they can even know my changes of emotions. So there is what we call emotion mining. You can find the emotions of people and target you based on your emotions and the time and so forth. So imagine now how much data they need to collect and integrate. That's what we call big data. This is the pieces that some belong to me as a company, what the customer gave me, but some doesn't belong to me. I go elsewhere and I collect it. I have to do linking of the records, and I create knowledge that I didn't have before. And this knowledge is being created today and is accessed by many entities, machines included. So the machines will have more information than what we have. I mean, I can't read all this, but the machine can. The reality is a little bit different. So I'll make an analogy with the car industry. So in order to drive a car in the beginning of the 20th century, you needed to be almost an engineer. You needed to know how to fix the car if it breaks down, and so you needed to know the details. Today, you don't need to know how the car functions. You don't need to know what is a carburetor. You don't need to know how the distribution of the power goes to the different spark plugs. You don't need to know how the gas is mixed with air. All that is irrelevant to you. You actually just press a button, start. We used to have a key. You remember before the key, we used to have a crank. Used to be, I mean, you had to be strong to turn that. So the constraints changed. And that is what is happening with big data today. So we are still in the beginning where you need to be an engineer to work with that car or drive it. We'd like to be able to have a car where you press a button and the machine will tell you everything you want. We're not there. The truth is we're actually even way beyond the Model T. Before that, we are at this level, and we'd like to go to the car where you just sit in and it takes you where you want. Okay, we have a long way to go, but we are getting there. And my argument is that what we will reach to at the end with this big data will be part of the equation for the singularity. Oh my! So here are the paths to the singularity that I consider. Often people think about one of them, which is that the machine will become more intelligent than the human and will drive innovation after that. Actually, there are 4 paths. One is not really realistic. So biology will allow us to improve and becoming intellectually superior. We'll have to wait millions of years. Why millions of years? Because I think if you take even Aristotle, and if he was born today, he would be as intelligent as us. Evolution is very slow. We can't really make it faster. Oh, can't we? People are actually trying to think about it and think about how we do selection to help biology so that people who have diseases, we know them before they are born, we just eliminate them and keep only those who are healthy. Is that ethical, unethical? There's a big discussion about that, but people are considering it. The second path is the one that most people think about, is create an artificial intelligence that will exceed the human intelligence. I argued that we're almost there on the hardware side, but the software side, where it's still far away. It will be possible the day when machines will write their own code. If machines write their own code, maybe that will be faster, but we're still way behind on the software side. The third path is actually the most exciting one, and I think it should be exciting for all medical doctors, all the people who are in medicine, because it's the path where we will mix machines and humans, the cyborgs. So we will use machines to augment what we can do. And that is very possible, and I'll show you some examples. Okay. And the fourth path is something that I believe is also very plausible. It's when you have a network of small entities put together, collectively they can create a new form of intelligence that individual machines don't have, but put together they may have. We still don't know how to control it, we still don't know how we can express it, but it exists already in nature. So one thing that will help going towards that is what we call the Internet of Things. We're already connecting many small devices together, and they communicate in different ways, and they exchange different things. But in nature, if you look at ants, I don't know if I have the chance to show you the video. So anyways, I invite you to go and see that video. It's fascinating. Because you realize this is the complex structure that is underneath, and on the top you just see the hole, but the colony is very complex, and you can't conceivably think that an ant would know this whole thing and build this architecture. Each one knows a tiny bit and does its job, and collectively this happens. So it's the intelligence of the collective that designed it. It's not one ant. And it's the same thing with computers. So how they communicate and how they know all this information collectively, or how they know part of it and mix it, and that's still unknown. But machines can eventually do it, and another kind of intelligence can emerge from a set of machines that are connected. And that could be a form of singularity. So where do I stand? I'm in computing science. And I'm doing data mining, but I definitely can't pretend to predict the future. But in my view, the technological singularity will happen in some future. When, I don't know. Not in a very near future like people are claiming. They're saying it's 21st century. I don't believe it. There are many things missing. The day they happen, maybe it'll be sudden, like some people have said. Will artificial intelligence play a role in the singularity? Definitely. It's it's the main ingredient to reach it. The problem is that what we call artificial intelligence is a moving target. What we used to call artificial intelligence yesterday, it's not what it is today, and it won't be the same tomorrow. And I'll mention that when we talk about artificial intelligence. Are there dangers? Is there something that can be problematic for us? Yes, and we'll have to be ready for it. How? Well, first we have to think about it, realize that it can happen, and what are the risks, and then consider those risks. So should we build warning systems? Should we put some limitations? Should we create rules, regulations? I don't know. This is something we, as a society, we have to think about. I want to mention about cyborgs. This is one of the paths, the third path that I mentioned. There are two kinds of cyborgs. I will go through this slide. So cyborgs is when you mix human flesh with machines. But you can also mix machines with flesh. So here are examples. So we have actually cyborgs among us today. We have hips, we have artificial knees, we have, we already added many prostheses to people, like the cochlear implant, whatever, you name it. But there's another path to cyborgs. You can add to machines some cells. And this has been done. I have a video showing a robot rat. So they build a robot, but the processor controlling the rat wasn't the processor. It was a set of cells from a rat brain. So they took a rat brain and they controlled that robot to learn how to go through a maze, for example. The beauty of this is that after the cells died, they replaced them with new cells, and the robot had a different behavior. So even though you have like cookie cutters, the robots look the same, they have different personalities, which is amazing. Amazing thing. So anyways, you can have cyborgs from both sides, and this is the subject of many, of course, science fiction movies, but who doesn't want to be the $6 million man? There are many, many movies of these cyborgs that are way more powerful, have more capabilities than the other humans. I think I'll stop here and I'll talk about the augmentations another time. I'd like to give you some time to ask questions if you have questions.